So in today's video, we will try to understand a very important observation which we have encountered till now while understanding the concept of entropy and information gain. And we have observed in all the numerical examples we have solved till now that the entropy of the node decreases after a split is performed. And this is precisely what we are going to prove today. This is a statement that show that the entropy of node never increases after splitting it into smaller successor nodes, and it's from the same book as we referred in the previous video, Introduction to Data Mining, by Tan, Steinbach and Kumar. So let's try to approach the problem with a numerical example first, and we will try to generalize the result in the process. So in this numerical example, we consider only the specific feature which we will be using for splitting the decision tree further. We assume that there were many features in the data, and based on the best information gained, we selected the feature X for splitting the data. We can see that we have 17 observations, out of which 7 are negative classes, which will correspond to the target Y being equivalent to 0, and 10 are positive classes, that is the value of target Y is equivalent to 1. So based on distinct values of X and Y, we can define two random variables X and Y as below. So X is a random variable denoting the occurrence of distinct values of feature X, and X can take only two distinct values A and B, and Y is again a random variable denoting the occurrence of distinct values of target Y, and Y can take only two values again, 0 and 1. We will try to find out the joint PMF corresponding to the random variables X and Y from the data which is given to us. We can clearly see the table over here. So if I have to generalize the value which I am getting over here, this is exactly what we can say is equivalent to probability X as A and Y as 0. And if we consider all the 17 observations which we have and try to find out the combination of X being equivalent to A and Y being equivalent to 0, we will exactly find only 4 such combinations which are precisely over here. So this is the third one, and eventually this is the fourth. Likewise, this 5 by 17, which we can write as probability X equivalent to A and Y equivalent to 1. And now if I try to find out the possible combinations in the entire data set, when X was A and Y was 1, it is 5 by 17 over here. Like there were 5 occurrences out of 17, and hence we get the probability. Likewise, we get the similar probabilities corresponding to the value of X being equivalent to B. Now since we get a joint PMF, we can clearly see the marginal PMFs, and it's pretty simple over here. Like this is the marginal PMF corresponding to random variable X, and this is the marginal PMF corresponding to random variable Y. All we need to do is for X, we need to add up across a row, and if we do this add up, we will be adding up the distinct values of Y which it can take corresponding to X being equivalent to A. Then we can use the probability theory to say that 9 by 17 is actually the probability when probability X is equivalent to A, and likewise 8 by 17 is the probability when X is equivalent to B. And this is exactly how we are able to find out the marginal PMF of Y. For any value of Y, we can actually sum over the distinct values taken by X, and we get the marginal PMF as shown. Like the 7 by 17 is obtained by summing over the distinct values A which X can take, which is A and B, and the 7 by 17 is probability of Y being equivalent to 0. So when I add both these terms, I get this as a marginal probability. Now this was all based on basic probability theory. Now we will move a step further and try to define the entropy which we have been studying till now. So whatever we studied till now, was precisely the entropy formula which I have written over here, but in a random variable form. Initially, we used to write things like P1 log base to P1 or P0 log base to P0, and that P1 or P0 was actually something like probability y equivalent to 1, and similarly P0 was probability y equivalent to 0. So we write it in a pretty standard format. We are just writing it in this format, and then we use the same results as we derived a step before and replace probability of y with the summation over x. This is what we get over here. So we knew probability y is equal to small y is a term which we defined, which we actually derived a step before, considering all the distinct values x can take. We are just plugging that term over here, and the end result is we are getting a double summation over here, 1 on y, 1 on x, and the log term remains as it is. We are not going to change the log term as of now. So one important thing we need to note over here is the fact that this result can be generalized for more than two distinct values of x. We had only two distinct values, a and b, but in case we have n distinct values of x, a1, a2, a3 up to an, it can be generalized for that as well. And when I'm talking about generalization of result, I am referring to this entropy before split, e1. And also for more than two classes in the target variable, this result could be generalized. Since we are performing a split based on two distinct values of x, we get the entire dataset distributed in two parts. This is the first dataset where the value of x is all equivalent to a, and this is the second subset of the dataset, original dataset, where the value of x is equal to b. Now we will try to calculate the conditional probability distribution, which we are going to use in the further calculations. So this is how the conditional probability table will look like. A value of 4 by 9 is aptly defined over here. So this should not be confused with the marginal or the joint probability table which we drew a bit up. So this was the joint PMF. It was taking into account the combined occurrences of A and 0 together. But over here, the table which we are considering over here is implying that we need to find the probability y is equivalent to 0 given the value of x has already been attained, and this is ideally a scenario which happens when a split has already been made. Now if I have to calculate the entropy values similar to the way we had been doing till now, this is exactly how we will be calculating it. Over here, if you carefully notice, the value of 4 by 9 over here is a conditional probability. Like we first assume that the value of x being equivalent to a is taken, and then we try to find out what is the probability the target is going to be 0. Likewise, the value of 5 by 9 is again a conditional probability. Over here, it means that the value of a is already taken by the feature, and what we want to know is what is the possibility of y taking a value of 1, and then we find out the entropy corresponding to a. Exactly, we are going to do the same step over here, but we will be generalizing it a bit. So we always used to write P0 over here, we used to write P1 over here. Formally, these terms P0 and P1 will mean this, like this entire term is what we called as P1, and this entire term is P0. Just that for notational convenience, we write things in the way we do in our calculations, but if we have to formally write it, so P1 over here, if we consider the entropy corresponding to attribute value being equivalent to A, it will mean that the target takes the value of 1 given the attribute value is A, and similarly the target will take the value of 0 when the attribute value is A. And if we proceed in this way, we get entropy corresponding to A as this. Now this is exactly what we will be doing for the calculation of 0.99108. And this is a much generalized form of writing the entropy corresponding to one of the distinct values of the feature x. It can have many distinct values, but as of now we have just two distinct values for understanding purpose. So we can proceed and calculate the entropy when x is equal to b in the same way. So the entropy corresponding to x being equivalent to b is calculated in the exact same way, which comes out to be this. Now you see that if I follow this table, I was able to find these two values. I know these two values, 9 by 17 and 8 by 17, and if we look a bit carefully in our marginal table, which we were able to define in the beginning, this is exactly the marginal distribution of x. Like what is the probability x takes the value of a, and what is the probability x takes the value of b. So from what we can see is we can calculate very well the entropy which we are getting over here. So if we have to write it formally, this is how we will be writing it. So the entropy of child node on splitting will look like this. This nt by n which I am writing over here, this is the probability value which I just discussed, and similarly this is the probability value, and corresponding to that we multiply with the entropy, which is EA and EB, which we obtained respectively over here and here. So these were EA and EB values. This is exactly how we are trying to obtain the entropy of child node of splitting x. So there was a parent node, and we use the distinct values of the feature x, which is a and b, and then we were able to obtain the child nodes. Now in the calculations further, I am just plugging the value of ea over here. So the value of ea is obtained over here. I just plug in as it is, and similarly I plug in the value of eb, which is obtained over here. So on doing so and simplifying further, I apply the probability of I apply the conditional probability rule, like probability of y equivalent to y given x equivalent to a is written as this: probability y is equal to y intersection x is equal to a, and in the denominator we get probability x is equal to a. And if you see carefully, these probabilities get cancelled out, and the similar scenario happens when we expand the conditional probability corresponding to b. This probability x is equal to b will get cancelled out. Now on solving further, what we can see is we have a term over here after cancelling the probability x is equal to a. This is the term which we have, and similarly this is the term which we have from the second term of the expression. Now if I combine both the terms together, we can generalize it in a much better way, because if you see this entire term carefully, along with a, like probability of y equivalent to y, x is equal to a, we are observing the same sort of probability in logarithms as well. Like I am using log to the base 2, the same index of x is being followed over here. Likewise, the same index of x is being followed over here as well, which is equivalent to b. And now I can club both the statements together and get the final result, which will be looking somewhat like this. Now we were able to find out the entropy corresponding to the child node, and we were able to find out the entropy corresponding to the parent node as well. Now let's take a break and review what all things we have done till now before we proceed further. So we needed to prove this assertion that the entropy of a node will never increase after splitting it into smaller successor nodes. So this could be done by first finding the entropy of the parent node, and or the entropy before performing a split. This is exactly what we did over here. We were able to find the entropy before split, which was pretty much generalized. Even though we started with an example for our own understanding purpose, just to illustrate how we are able to get a PMF from a joint PMF, I created this numerical example, but the result obtained over here is pretty much a generic result, independent of the distinct values x can take. So this is the E1, and if I see my proof statement which we needed to prove, So this is going to be the entropy of my parent node. So this is what we needed to prove, that the entropy of a node will never increase after splitting to smaller successor nodes. Now we have the entropy of parent node as E1. We will try to split it and get the entropy of the child node, and then we will try to understand what is the difference we are getting. Now on splitting the data, based on the distinct values of x and y, we were able to get this conditional probability table, and the way we used to calculate the entropy in all the video lectures till now, we were able to write it in a much generic form, and the eventual result for the entropy came out to be this. So this is the entropy of the child node on splitting x, and this is also pretty generalizable. If you see this, it doesn't depend on only two distinct values of x, it can depend on any distinct values of x. Now I have two results, E1 and E2. So E1 I have, this is the entropy of the parent node, and E2 I have the entropy of the child node. What we need to prove is the entropy of the parent node is always higher than that of the child node, or there can't be more randomness after splitting a parent node. So this is what we need to prove. So we will try to find the difference between E2 and E1, or at least try to find an equation which will give a relationship between the two. So we plug in the values of E2 and E1 over here. This is the value of E2, this is the value of E1, and we are, since the term outside the logarithm is exactly the same, we can take this term common out of these two expressions, and then we try to solve for the values inside the logarithm. So this is what we are getting: log to the base 2 probability y equivalent to y, and this is the log to the base 2 probability y given x, which came from here. So now we know that we can now use the property of logarithms to simplify it further, and on simplifying, we are getting something like this, like log a minus log b is equivalent to log a divided by b. This is exactly what we used over here. Further, we try to implement the conditional probability rule over here. Like, we know the probability of y given x, this is equivalent to the intersection, and the denominator will come in the numerator, and eventually we get an expression which looks like this. So even though we have reached till here, but still we are far away from reaching to our goal. So we will use a property of convex function over here. So we can clearly see that if we define a function fz, which is logarithm base 2z, and we take the double derivative of fz, which will be equivalent to minus 1 upon z square, for all z being greater than 0, fz is f double dash z is going to be less. So whenever such a thing happens for any function f is said to be a concave function. So I will link up the definition of both convex and concave function over here, but since this property will be used extensively in simplifying the statement, this uh, calculation further, I will just state it over here and use the results as it is. So we will use the following property of concave functions, which is nothing but the definition of concave function. The only constraint we need to consider is the fact that summation ai should be equivalent to 1. So on doing so, we get a result which looks like this. So we are going to use both this result which we have obtained over here, and the result which we were able to find out just by using the definition of logarithms to get the next step of our calculation working. So this is what we are trying to say, that since we had the constraint over here that summation of all the AIs should be equivalent to 1, we don't have to worry because we have probability, a joint PMF over here, and the summation is happening on both the random variables. So we can replace the AI with the probabilities, and similarly we can replace the ZI over here with the term which is inside the logarithm. So we can replace Zi with this entire term, which I am highlighting over here. So on proceeding further and applying the non-convex formula over here, we get this as a result. So whatever was in the form of summation ai log zi, it's now in the form of log of summation zi, and of course an inequality comes into place, which happened because of the concave function property. Now if I solve it a bit further, I am able to cancel both the terms out. This term and this term will get cancelled out. We are left with product of two marginal distribution which are independent of each other. Now, if I apply the summation on both of them individually, then we know that summation of the marginal distribution of x and marginal distribution of y is equivalent to 1, because that's how the PMF were defined. And eventually we come up with this, that this is equivalent to 1, this term is equivalent to 1, this term is equivalent to 1, and eventually we get log base to 1, which translates to 0 over here. Now, if we see the equation over here, what it means is E2 should be less than equivalent to E1. And this is exactly what we needed to prove in the beginning. Now, if I go a step back, so we needed to prove that E1 is greater than E2 or E2 is less than E1. We started with the difference between E2 and E1. Both E2 and E1 were derived before, and we proceeded further, and we were able to come up to a point where we were able to attain an expression for the difference between E2 and E1. The only advantage we got from here was the fact that log is a non-convex function, and we use the property of concave functions over here to get the results, and eventually we found out that E2 is less than E1. Entropy of the parent node is always higher than that of the child node. Now what it means is the fact that if I am able to write info gain over here, so this is equivalent to E1 minus E2. Since E1 is greater than or equal to E2, so E1 minus E2 will both be greater than equal to 0. This will mean that information gain can never be negative. The least value information gain can take is 0. So this concludes our discussion about information gain and entropy. And in the entire span of around 6 videos, we captured every possible aspect of information gain and entropy as we could. So in the next video, we will be talking about another important metric, which is gain ratio. Thanks for your time.